Okay, let's launch into our discussion of eruptive styles and landforms that result from volcanic eruptions. So we're going to talk about 5 different shapes of volcanoes that form from centralized eruptions coming out of one lava tube. And the main 2 are going to be shield volcanoes and stratovolcanoes. And then these other 3 are going to be more minor. But when we think about shield volcanoes, we want to think mafic composition. We want to think shallow slopes and less dangerous eruptions. Stratovolcanoes are volcanoes which form from intermediate or felsic. They tend to have steeper slopes, and they're much more dangerous. Let's look at these in detail. So a shield volcano is a very large volcano forming from successive layers of basaltic lava that have been erupted on the surface. One good example is Hawaii. The entire big island of Hawaii, and really all of the islands of Hawaii, are individual shield volcanoes. They have very gentle slopes to them because the lava, the basaltic lava that forms them, is not viscous, so it can flow easily. And you get thousands upon thousands of these eruptions stacked together over time. You form a very large volcano. So here's a little diagram of what one of those look like. When we talk about the volcanic crater, that is a depression that sometimes forms, not always, but often does form at the center, the highest point of a volcano, and it connects to that central vent, which is the main vent that feeds up from the magma chamber. Right, so this is 60 kilometers wide, that's tens of miles wide. And each layer on this is going to actually be hundreds of thin basaltic lava flows. Thin, again, because it's not very viscous. On the island of Hawaii, and on most shield volcanoes, you're not going to have eruptions forming from one spot, but there can be side vents as well that erupt at the same time. In contrast are stratovolcanoes. So stratovolcanoes are much steeper, something like Mount Fuji in Japan, or Mount Shasta in California. Mount St. Helens was another example. There are a lot of examples in the Pacific Northwest like this as well. Mount Hood, etc., Mount Rainier. All of these are stratovolcanoes. They're steep-sided volcanoes, they're intermediate or felsic in composition. They again have central vents and often side vents. But because they have intermediate or felsic composition, they can often erode more explosively, and they're in between the lava flows. You often have layers of pyroclastic material. So our shield volcanoes are almost entirely built out of basaltic lava flows. These are built out of a combination of lava flows and pyroclastic layers. Things like the tuff that we saw, or the volcanic breccia. Deposits that are formed from stuff that was thrown out into the air really violently. They often also have a central vent that's been filled with lava from the previous eruption that is solidified, and that volcanic plug is part of what holds back gas pressure and causes these to be very explosive eruptions. So, contrast stratovolcano with the shield volcano that we just talked about. Let's talk about some other morphologies that we'll see on some of these volcanoes. So a volcanic dome refers to a part of another volcano that often forms inside a collapsed crater from a volcano. So these are just little domes that form on top of a central vent from pretty viscous magma, right? So viscous, felsic, right, rhyolitic type lavas that pile up over that vent. It might still be erupting like you can see here, but they tend to pile up and they don't flow out all across the slope. So for example, you see Mount St. Helens here. This erupted in 1980, killed dozens of people because you can see that it blew off this whole side The whole flank of this volcano collapsed as a result of this really powerful eruption. And then as the eruption trickled off later in time and just erupted a little bit at the end of it, it built up this volcanic dome in the center of its crater. So you can see a volcanic dome on some craters, or on some volcanoes. A cinder cone volcano, sometimes these are isolated by themselves, sometimes they are on the flanks of other volcanoes, but these are tiny little volcanoes, relatively speaking, tens to hundreds of meters across instead of many kilometers, that are built out of volcanic cinders. So these rocks, these cinders that they're built out of, are often somewhere between pea-sized and fist-sized. And these are a rock that's called scoria. It's very similar to pumice, except that they tend to be more mafic than pumice is, and as a result have larger bubbles. The gas is able to move through that cooling lava and collect into these bigger bubbles instead of pumice, where the bubbles are very finely distributed. Like scoria, pumice is very low density. It can often, it often still sinks in water, but it's much less dense than many other rocks because of all those bubbles in it. But these tiny cinder cone volcanoes are built out of these piles of scoria, or cinders, as they're often called sort of colloquially in the US. And they're built almost entirely from these right, they're pyroclastic. They've got the bubbles in them that's suggesting that they've been thrown up into the air. Cinder cones, thus called because they're built almost entirely of piles of cinder. It's as if you just took those cinders, these pieces, and just plop them down. It's generally not solidified around there. Now, what else can erupt? Sometimes you'll have a ring of mafic lava that sort of trickles out underneath these, because there are going to be gaps and pores in between all of these cinders after they've been piled there. But for the most part, these are built as pyroclastic debris from a small eruption. And there are examples of these that are actually, they can build over human timescales. There was an example in Mexico. I'm not sure if this Cerro Negro, no, that wasn't where it was, but this is talking about Nicaragua. There's an example of one volcano in Mexico that formed from an entirely new fissure in the middle of a farm field over the course of tens of years, where it just started erupting one day, tossed these out. Now, they are pyroclastic, so they're dangerous, but these are relatively small eruptions, so it's not affecting a large area. And this pile built up over tens of years into something about the size of what you see here. But cinder cone volcanoes tend to be very tiny. Sometimes they're on the flanks of other volcanoes, and they tend to represent sort of a very small eruption. Calderas, on the other hand, are often the result of a very large set of eruptions. So calderas are these collapsed areas that result when a violent eruption empties a volcano's magma chamber. So this empty chamber down here is left behind. And because it's empty, there's no material there that's supporting the overlying rock, which then collapses. That leaves this large, steep-walled basin. So an example of that is Crater Lake in Oregon. It's a bit of a misnomer when we talk about Crater Lake in Oregon, because many volcanoes have craters at the top, but this is generated by the collapse of an entire magma chamber. So this really should be called Caldera Lake. And you can even see another little, a little volcanic cone that's forming there. What would we call that? This little cone that's forming inside of a bigger one? We'd call it a volcanic dome, right? So we can see this volcanic dome forming inside Crater Lake there. But this resulted from a very large eruption and a later collapse. And often these calderas are filled with lakes. But in the case of really large ones, like the Yellowstone caldera, they might only be partially filled. So Yellowstone caldera is more than 30 miles by 40 miles in size. If you go to Yellowstone National Park, a large part of it is this caldera, which I'll outline here. This resulted from a huge eruption. It is a hotspot volcano forming on a continent, so it's got a weird mixture of different lava flow types. But this is a major volcano, and should it decide to erupt again, you can imagine that a volcano with a caldera that's 30 by 40 miles wide that erupts explosively could really do some damage. So we talked about the two main types, shield volcanoes and stratovolcanoes, and then three more minor types. Let's compare side by side the relative sizes of a lot of these. So cinder cones are tiny. This is a large example of a cinder cone. Some of them are much smaller. Going up from there, you have a set of different stratovolcano sizes. They can range in size 5, 10 times, but then the largest stratovolcanoes are still going to be smaller than the smallest shield volcanoes, ones like Kilimanjaro there. And then a really large shield volcano example is Hawaii. So let's walk through the formation of one of these and walk through how something like Crater Lake in Oregon would have formed. So first, fresh magma would fill a magma chamber. Eventually you get a volcanic eruption triggering. It's a very explosive eruption, and we would have called it, like we call it the ancestral Mount Mazama, that would have collapsed ultimately to form this lake. So this Mount Mazama, we can tell it built a long time over time because we can see lots of these different lava flows recorded in these layers. Eventually, though, the magma chamber would have become partially depleted, would have erupted several times, becoming smaller and smaller, but we can see that this magma chamber is starting to deplete already. Eventually, the summit of that mountain is going to collapse into that empty space that's left behind. When this collapses and forms a caldera, it would have generated large pyroclastic flows, lots of ash being tossed out as this happens, surrounding an area hundreds of square kilometers. So we can see evidence of that pyroclastic layer from the collapse in the area around Crater Lake. Eventually, those pyroclastics settle out. Because this is a depression on the land surface, it can be filled in by rain, and a lake is going to form in that caldera. As that residual magma, whatever was left, cools, you might have some minor eruptions, right? So you have some hot springs forming, some gases. A small volcanic cone then would have formed in the caldera. We might have called that a volcanic dome. But this is only the little bit of remaining liquid that is erupting after most of the eruption has ceased and that magma chamber has collapsed, forming this caldera. We call it a crater, but really, if I ask you what Crater Lake in Oregon is, you shouldn't say a volcanic crater, you should say a caldera. So volcanoes aren't actually the only way that you can get lava erupting on the surface. You can also get eruptions that are formed from linear cracks on the surface, forming things like fissure eruptions, or flood basalts, or ash flow deposits. So let's talk about one of these fissure eruptions might look like. So in Iceland, what's the deal with Iceland? It's at this divergent boundary. So it's being fed by magma along a whole line of this boundary, right? And as a result, in some places, you get entire fissures opening up, many, many miles long. And so at this location, it's a divergent boundary. What type of lava is that going to produce? Mostly basaltic lava. And it's going to flow out on the surface relatively gently, but it's going to flow over a very large area. So one place that you can see these fissure eruptions from a linear feature is in Iceland. We can think about the sequence of events that would form one of these fissure eruptions. So this very highly fluid this low viscosity basaltic lava flows across the surface. And as it flows out, rather than forming one isolated mountain, it's going to flow in both directions away from it, away from this fissure, generating these very widespread flat layers. You might see some isolated cinder cones on there, like we saw in the previous image, that are much smaller. And they're the remnants of the last bits of eruption as these layers are forming. But because these large fissures are feeding a large area, it's going to cover a large area. An example of what these can look like on a very large scale are these flood basalts. And so Earth has several places covered by flood basalt that can cover a huge area. Like you look at this area in the Columbia Plateau in Washington and Oregon State, this covers a very large area, right? Hundreds and hundreds of square kilometers. So if this is actually 400 kilometers across and that's 300, that's what? 100,000 square kilometers. It's a huge area. And these can be more than a kilometer thick too. You can see some of the layers that this formed from successive layers of flood basalt deposits. Like here's a layer, here's a layer. And these, they look sedimentary from a distance, but if you get up and actually look at them, it turns out that these are actually igneous rocks. They're flows of basalt. So these all formed roughly 15 million years ago. And we think that they may have been fed by the same flows that are now feeding Yellowstone, just at a different phase of that eruption. So they're generating large flood basalts instead of isolated explosive eruptions like have happened in Yellowstone in the past couple million years. Let's talk a little bit about the interaction between the volcanoes and hydrosphere and the atmosphere in different types of eruptive styles. So if we talk about eruptions that are really only releasing gas emissions, they're called fumaroles. Whereas geysers are places that hot liquids get erupted. Largely, these geysers are fed by the surface hydrosphere, so that water is coming from groundwater that's interacting much more recently with things like rainwater. It's not actually coming, the water itself is not coming from the magma itself, but it is percolating deep enough that it interacts with magma, or at least hot rock, and then it turns to steam and it comes out on the surface. I'll also talk a little bit about aerosols and ash here. So here's an example of what a fumarole looks like in Indonesia. And these volcanic gases are spewing forth from this fumarole. And what do you see them leaving behind? What is this bright yellow mineral being left here? Sulfur. These volcanic gases can have a different sulfur-containing species in them, like H2S, SO2, that leave behind this sulfur deposited on the side there. They can also have things like, there's a lot of CO2 in these gases, sometimes methane as well. Some gases containing chlorine or fluorine that are also acids. Here's an example of a geyser. This Old Faithful geyser in Yellowstone National Park, so named because it tends to erupt pretty regularly with relatively consistent timing. And actually, the timing used to be more consistent than it is today. But what's happening is this geyser is being fed by water that rains on the surface, percolates down underground, heats up, and then gets spewed forth when enough water vapor pressure builds up. Ash and aerosols are an interaction between the volcanoes and the atmosphere that we want to talk about. And I just want to mention what the difference is between something that's called ash and things that are called aerosols. So ash is fine solid particles, fine enough that they can be carried by wind, but they can be visible in some cases, right? Very fine sand to silt size. But eventually they'll settle out. Whereas aerosols are so tiny that they stick around in Earth's atmosphere for a long time. They're less than 1 micron in size. That's 1/1000th of a millimeter, or 1/millionth of a meter. So these are very tiny particles. To get an idea of what something else that's an aerosol that you're probably familiar with, mist and fog are these non-volcanic aerosols. They're very, very fine distributions of water droplets. Those water droplets in mist and fog are less than a micron across generally.